Hi, everyone. Thank you so much for coming to our second virtual Astronomy on Tap here in Baton Rouge. We hope that you're staying safe and getting prepared for our, imminent hurricane, whichever one it is this year. I can't keep track. Again, we're so happy to have you guys here. We have two awesome speakers for you today. We have Dr. Colin Turley and Dr. Donna Pierce. Today, we're going to go ahead and start off with just introducing our tip war again. So, of course, as per usual, we have our tip war going on. And how we're going to do that is you can donate to either our Venmo or our PayPal, which you've likely seen on the slides that have been going on for a little while. This month, we're asking you whether you think the recent detection of phosphine on Venus is indicative of life or not. So for some context, there was a recent press conference regarding detection of a very rare molecule called phosphine up in the cloud decks of Venus in the atmosphere. The only way that we currently know to create this rare molecule is by biological processes, but a lot of astronomers are still skeptical. So let us know what you think if you decide to donate, and we would be very happy to hear from you. So we're going to go ahead and get started with our first speaker, Colin Turley. He is our newest faculty member at LSU Astronomy and Physics. He did his graduate studies at Penn State, where he says he liked to watch the football games from above in a nearby mountain. He also has the Zelda Ocarina of Time puzzle-solving theme as his ringtone, so make sure you listen for that while he's talking. And with that, here is Colin Turley.
Hello, everyone. My name is Colin, and I'll be talking to you tonight about how to see the most extreme events in the universe, namely, an introduction to multi-messenger astrophysics. So that name right there is a bit of a mouthful by itself, so I'll have to break it down a bit and discuss it, and then discuss what you can do with it. So, first, a bit of the structure of this talk. Tonight, first I'll introduce the four messengers, aka what is multi-messenger astrophysics. And then I'll talk about it in the context of three different systems, namely supernovas, active galaxies, neutron star mergers, and then I'll give you some conclusions, and you can ask all the questions that have occurred to you over the talk. So, first things first, our introduction, the four messengers. So when I say a messenger is a way of looking at the universe. So a multi-messenger event is simply any event you observe in space or in the cosmos with two or more of the fundamental messengers. So these messengers are photons, neutrinos, cosmic rays, and gravitational waves. So you might be familiar with some of those. You might not be familiar with most of them. The one everyone is familiar with is photons. Everyone is familiar with photons because they make up visible light. So these are the four different messenger ideals that you have in astronomy. You can see something in any one of them individually, and if you see it in all four of them or in any two of them, that makes it more interesting because suddenly you have a multi-messenger event. So now to explain why this matters, I'm going to dig into a bit of what each of these messengers means and a bit about why it's interesting to look for things in combination. So to start off, we'll go into the easiest messenger to understand, the photon, aka light. So when we look at the electromagnetic spectrum, we're seeing a narrow range of it, this narrow range called visible light. Visible light extends between 800 nanometers and 400 nanometers. That is just a range of light where our eyes are sensitive to it and we can see it. Thing is, light extends far, far off of that. You can go to a shorter wavelength, higher frequency, higher energy to the ultraviolet light. You can go lower energy, longer wavelength to the infrared light. Night vision goggles see infrared light oftentimes so you can track heat in the dark. Ultraviolet light is notable for giving people sunburn. But you can extend the spectrum far off that, down to microwaves, up to gamma rays. And basically, it's just a giant spectrum. And once again, every object will shine in a different part of the spectrum depending on how hot it is. So if you're around 10,000 Kelvin, hotter than the sun, you will shine primarily in the visible light spectrum. If you get hotter than that, into the millions of Kelvin, you'll shine the X-rays. If you get colder down to like 1 Kelvin, you'll shine the microwaves. You can also talk about this in terms of energy. So since light is a collection of particles called photons, each photon has an energy associated with it. That energy is affected by what color it looks. So visible light, for example, has a photon with between 1.5 and 3 electron volts worth of energy. It's not a lot of energy, but once again, that's energy of an individual photon. But the energy of a single particle is often useful to measure that way. So visible light, around 2 electron volts of energy per photon. Go up to something like a gamma ray, and you can easily have 10 to the 6, 10 to the 10 electron volts per photon. Radio waves, you can easily have 10 to the -9 electron volts per individual photon. So it gets the idea that the spectrum is broad. But why do we care? What's wrong? Why do we care about more than just visible light? Well, to answer that, we need to look at an object. So behind me on my background is the Crab Nebula. It was formed when a massive star exploded back in 1054. The Chinese saw the star explode, and they then talked about it, wrote about it, and when modern astronomers looked at the location of that exploding star long after, they saw a glowing nebula that we call the Crab Nebula. So in visible light, it looks much like the picture behind me. You see a collection of colors, light, and different sort of filament-like structures caused by the exploding star. But if you change wavelength and go to a different kind of light, it reveals more information. So in radio waves, you see a more diffuse collection of things. You can see you can see temperature by looking at the infrared image. And most notably, X-rays show you something more interesting, show you some strange structure you wouldn't think otherwise would exist. So visible, you don't see anything near the center of it. You just sort of see a sort of roundish object around some bright center, and you have colored gas on the edges. But if you look at it in the X-rays, you see some interesting structure. You see this sort of central dense blob and a sort of spiral structure around it. So if you look at it under Chandra, you can see that not only does it look a little bit different, it looks quite different. You're seeing that there's some other structure, some other features to it that you couldn't have seen just using visible light. Basically, by expanding your sense of what you're looking for, by looking for more than just one wavelength, more than one set of wavelengths, you greatly expand your understanding of what you're looking at. So that's just multi-wavelength astronomy. Expanding your wavelengths, you get more information. Go to X-rays and you can see this glowing lump at the center of the Crab Nebula that you couldn't see in visible light. So the same also holds true if you go into the other messenger particles. So that is photons. And now let's talk a bit about cosmic rays and about cosmic rays. So we actually have been observing the effects of cosmic rays for a long time. The effects were first properly documented in 1795, when Coulomb, the man who has a unit named after him, the unit of charge, discovered that when he had an electroscope, sometimes it would randomly just discharge. It would randomly do a thing that didn't make sense. So he wrote about it and theorized that maybe his equipment was faulty. Later on, Faraday looked at the equipment and did it with better equipment and said, nope, equipment works just fine. It's not equipment. And it remained a mystery for a while why these electroscopes were just discharging randomly. Then Marie and Pierre Curie discovered something. They discovered that if you took an electroscope and put it near something that was radioactive, it would discharge. In other words, electroscopes randomly discharge because radioactivity. Thing is, that raises the question, what is radioactive that's causing things in isolated places to discharge? I mean, if you put, say, radium next to something, of course you're getting radiation. But if you're just, say, in the middle of a city, not near anything radioactive, what's causing it? So there are some theories. One of the prevailing theories in the early 1900s was that the thing that was radioactive was the ground. So that means some people want to test this. How to test that? Well, get away from the ground. So Victor Hess decided to test this out. He took 3 electroscopes up in a balloon and measured how they discharge at different altitudes. So he did multiple balloon flights. He did balloon flights during the day, during the night, during a solar eclipse. And what did he discover? Well, he found out that as you get higher up away from the Earth, the count rate you see increases. You see more discharges as your altitude goes up. And for this work, he earned the Nobel Prize because he demonstrated very conclusively that this radiation was coming from space, not from the ground, from space. Furthermore, since it came down to Earth at night, it couldn't just be from the sun. The sun might contribute to it, but it couldn't only be the sun giving off this dangerous radiation. So in other words, Victor Hess discovered radiation from space. So now what does that actually mean in important terms? It means that we have cosmic rays. A cosmic ray is basically a charged particle like an atomic nucleus or an electron that is moving through space at high speed. They have some amount of energy to them, and that's basically what a cosmic ray is. Now, we are not dead of space radiation because of two things. One, Earth has a magnetic field. Two, Earth has an atmosphere. The upper atmosphere blocks out particles, and Earth's magnetic field catches the lower energy cosmic rays. They get bent around, they start spiraling, and you see them interact with the atmosphere in the north and south, near the north and south pole. It's what causes the northern and southern lights. The sun produces a lot of low energy cosmic rays, though once again, low energy is still a bit of a ridiculous term in astronomy and astrophysics. We say low energy, that still means that the particles from the sun are still traveling at speeds of only a few hundred kilometers a second. And they have energies that are fairly low, relatively speaking. But you can extend your understanding and your range of energies quite a bit. So here I have a plot of cosmic ray energy ranging from 10 to the 9 electron volts of energy per particle up to the ludicrous 10 to the 21 electron volts per particle. There aren't many particles that way. As you see, the abundance of those particles changes. For example, at like 10 to the 11 electron volts, you see about one particle per square meter per second. But go up a few orders of magnitude and suddenly it drops down to one particle per square meter per year, or go even further, one particle per square kilometer per year, and so on, to even rarer and rarer events. So do we see particles at those super high energies? Yes, actually. A famous example was the oh my god particle, named because when people saw it, they went, oh my god, that couldn't have been real. But it totally was. It was a proton that hit the upper atmosphere above Utah back in the 90s. It had an energy on the order of 10 to the 21 electron volts. In other words, it was a single atomic nucleus with the kinetic energy of a pitched baseball. So space is accelerating particles towards Earth or just anywhere in ridiculous energy levels. Note that the strongest acceleration we can achieve for an individual particle on Earth is at the Large Hadron Collider, which gets two corresponding beams up to energies of about 7 TeV, 7 times 10 to the 12 electron volts. Whereas here, in space, you're getting particles over 10 orders of magnitude, up to 10 orders of magnitude stronger, up to 10 to the 21 electron volts without problem. Problem is, they're charged particles, and just as Earth deflects the low energy ones with its magnetic field, any charged particle bends in a magnetic field. There are unknown magnetic fields in space. Therefore, if we see a cosmic ray, nice, but we can't tell where it came from. Not very useful. They just get scrambled by the magnetic fields. No idea where they come from, but we can still get information about them, like the spectrum I have here. So that is the second messenger, the cosmic rays. Charged particles from space. We're protected by an atmosphere and a magnetic field. Without that, we would be very dead very quickly. So the next messenger particle is the neutrino. The neutrino is a very funky, weird particle. It's called the ghost particle. It's electrically neutral and extremely light. They were first discovered when studying beta decay. Beta decay is a process where one atom becomes a different atom. For example, carbon-14 will beta decay into nitrogen-14 after some amount of time. This is how carbon dating works. Berry artifacts will slowly lose carbon-14, and you can, by looking at how much it's lost, into nitrogen, you can tell how long it's been buried. So, given all of this, this led to the discovery that there's missing energy and mass in this decay reaction. That is in the form of neutrinos. A neutrino is just a simple, small, light, electrically neutral particle that is produced whenever something changes. If a proton becomes a neutron, it gives off a neutrino. If a neutron becomes a proton, neutrino. Any reaction that changes a particle's nature tends to involve a neutrino in some capacity. So that's all well and good, but the reason they're hard to discover is that they don't really commonly interact with ordinary matter. Most particles, if they go through you, they hit you and do something. Light hits your skin, it bounces off, and people can see you. The dentist sends an X-ray through your jaw and can map out where your teeth are and if you have a cavity or not. Problem is, neutrino, if I hold my hand up and do this, there's approximately 1 trillion neutrinos passing through my hand every second right now. Thing is, they do nothing. In fact, at most energy levels, a neutrino could travel through a light year of lead without interacting on average. So they're hard to see, but since there's a lot of them, eventually you will spot ones. And the nice thing is that as their energy goes up, they interact more strongly. So higher energy neutrinos are easier to see. So there are currently 3 known neutrino sources. First that we discovered was the sun. We noticed that you had neutrinos from the core of the sun. Second was a supernova back in the 80s. And last is the Blazar TXS 0506, which we'll talk about the latter 2 of those later. They are both quite important to this talk. But note that there's currently 3 known cosmic neutrino sources. Others are speculative. There's only 3 we've actually confirmed. Neutrinos also have the weird property that they actually change their identity as they move through space. So normally, if say I threw a ball, if I toss an apple to you, you expect to catch an apple. But neutrinos don't work like that. If you send a neutrino to someone, it'll often change its identity. It'd be like me throwing an apple to you and you catching an orange. Still a fruit, but it's a different fruit, which would be kind of weird. Neutrinos also have this property where they can change their nature in flight. If I shoot an electron neutrino at you, well, it'll pass right through you, but when it passes through, it might be a muon neutrino or a tau neutrino. So the different types of neutrino can all change flavor. They can change what they are as they move, which is unique to neutrinos. No other particle demonstrates this ability. So that's neutrinos. The problem with neutrinos is that they point back to the source because they move in straight lines. Problem is, we currently don't have any sources or any distinct sources. In theory, every particle we see came from some source. It's just we don't have a good reading on if there's any persistent sources or more than one particle from a specific source. So when you look at the neutrino sky, you get an image like this. A lot of specks from around the sky and no distinct sources. So we're still working on this, looking for neutrino sources. We'll get some eventually. But for now, if you want to get neutrino sources, you'll need to look for them in concert with other particles. And this comes down to a simple idea. If a source is accelerating cosmic rays, that has consequences. If you're creating a cosmic ray, that will create neutrinos and photons at the same time. So in other words, if you start looking for photons and neutrinos, and you look for them in concert, you see both of them from the same source at the same time, then you can make statements about a source creating it because you're seeing a coincidence. That's more powerful than just seeing one or the other. The cosmic ray might arrive at Earth eventually, but the thing is it takes a weird wonky path because it bends in the magnetic fields, and we have no idea how to measure the galactic and intergalactic magnetic fields. So that is the idea of the first 3. We know sources are creating cosmic rays because we see cosmic rays. We don't know where they come from because they bend. The acceleration should create neutrinos, and photons. So if you see both of those particles in a coincidence, you can deduce that it's a cosmic ray accelerator, even if you can't see the cosmic rays directly. So there's one last category of source we can talk about as well. The last category is the gravitational waves. They're most commonly created when 2 very dense objects are orbiting one another. A gravitational wave is basically a distortion to space-time itself. So here on the side of the slide, I have a ring of particles. The idea of that is, as a gravitational wave would pass through the screen into or out of it, the particles on that ring would slowly oscillate. They'd move in and out as the wave passed through. Obviously, that wave is very, very exaggerated. The reason it took till 2015 to discover them was that they are weak. Gravitational waves are not very big. They're orders of magnitude beyond the sensitivity of anything but a ridiculous instrument like LIGO, which we have one of the detectors only like 100 miles from here. So every known case of gravitational waves we have is due to black holes or neutron stars merging. In theory, if I wave my hand over my head, I'm creating gravitational waves. It's just they're so weak, you'll never notice them. But basically, they're created when two heavy objects spiral around one another. And of course, when the two objects spiral and collide, that has the potential to create other particles like neutrinos, photons, or even cosmic rays. So in other words, there's another messenger we can add to the puzzle of multi-messenger astrophysics. So the biggest problem with gravitational waves by themselves is they're hard to localize. Here are a series of images showing the sky localizations of different gravitational wave events. As you'll see, their localizations are kind of big. And this is just because narrowing it down to a single point is tricky without having a lot more detectors set up. With only two, you're at best going to get a banana-shaped ring in a banana shape or a ring in the sky. With three, you get a more localized location. And as you keep adding detectors, you get better and better pointing. But those are expensive. And so, in other words, your best bet for localizing it perfectly is to have an event happen. You see a general sky area from the gravitational waves, and then you zero in on that by using optical observations of the particles you're seeing, or maybe neutrinos. So gravitational waves by themselves give you a lot of information, but not everything. And to get everything, you need to look at other particles in addition. So let's talk about some of the three great trials of multi-messenger astronomy. So first of all, supernovas. The most famous of this is the supernova of 1987A. It was a blue supergiant in the Large Magellanic Cloud. It exploded back in the 70s, in February. Star exploded. Here's a before and after picture. On the left, you have the progenitor star, and on the right, the star exploded. It was bright enough you could see it with the naked eye. So this is all well and good, a very interesting event. So why was it so interesting though? Well, surprisingly, when the supernova went off, several hours before we observed it, we saw a neutrino spike in multiple neutrino detectors. Normally they see maybe a few particles a day. Suddenly all of them record like 8 to 10 particles all at once in a giant surge. And using a bit of data analysis, they reconstructed the neutrino location and found they came from this suddenly newly appearing supernova. So that information, this neutrino detection, let us understand the mechanics of an actual supernova. It let us realize that what happens in a supernova is the core of a massive star collapses as the star dies. And that collapse triggers the star to explode. And that explosion is so bright, the star will outshine a galaxy briefly. And it can be visible. And under the right conditions, the supernova can be visible during the day. So this also showed us the origins of heavy elements, because when a supernova happens, the fact that its core collapse lets us determine things about the elements that are created. In the explosion, heavy elements are generated, and that lets us figure out, say, where oxygen comes from. This observation of neutrinos let us model how, say, most of the oxygen that we breathe right now was once created at the core of a massive exploding star. The fluorine, aluminum, calcium, sodium, rubidium, krypton, arsenic, all those elements were at one point created when a massive star died and exploded in the process. So a multi-messenger observation in the late 80s let us figure out a process of how stars die and how elements are created. That's important. So that's one example of multi-messenger astrophysics. That's supernovas. Explosion, new elements, neutrinos. Other case you have are active galaxies. So in a galaxy, you always have a bright central region and some diffuse arms around it, or some diffuse structure around the central region. Thing is, in active galaxy, that central region is now really bright, as in abnormally stupidly bright. In the picture on the right, I have M87, a galaxy where the central region is very, very bright enough that if you say were in that galaxy on a planet, you'd probably be dead. Very dead. If the center of our galaxy went active for a little while, the intense radiation would be enough to sterilize basically every planet in the galaxy instantly. So they also produce these cool jet features. these long streams of relativistic plasma and particles getting shot out of the galactic core. So what's going on here? Well, in the central region of a galaxy, you have a supermassive black hole. In M87's case, it's about 1 billion times the mass of our sun. Supermassive galaxy, supermassive black hole means you have accretion. There are materials spiraling around there. As the material spirals in, it heats up to ridiculous temperatures. So hot that you're accelerating particles to ludicrous energies. They're interacting. And in the magnetic field, some of them get channeled into these giant jets. If you see this accretion disk, you see a bright point of light in the sky. If the relativistic radioactive laser jet from the black hole is pointed right at us, you have a blazar, a blazing active galactic nuclei. And that is an exceptionally bright object where you have extremely variable emission. The emission is tied to how much the black hole is accreting and accumulating matter. And you have just jetted emission from the black hole pointed right at Earth. Every blazar we know of is very far away, which is good because if they were close, we would be dead immediately. So galaxies create extreme bursts of energy from their center under the right conditions. And the jets just spew out radiation at a ridiculous degree. They're assumed to be sources of cosmic rays and probably neutrinos and definitely photons. But this wasn't confirmed until we reached the case of TXS 0506. So in September of 2017, the ice cube detector discovered a neutrino originating from this blazar right here. Exactly right time, right location, and it occurred when the blazar was in a flaring state, as it had been for the past month or so. The blazar was active, and it was 4 times as its normal brightness because it was active. It was eating more material, and that process, it must have spat out a neutrino, and we saw the coincidence. They did a lot of careful statistical analysis, a lot of data analysis, and after looking at these different regions, they found that yes, they can say this blazar, TXS 0506, in fact, is a source of neutrinos, and because it's producing neutrinos, it has to be accelerating charged particles, and therefore is also a cosmic ray source. We can't see the cosmic rays because of bending, but we can totally see the neutrinos as we have it on this one occasion, and we can see the photons. So we've identified that yes, active galaxies are a potential source of some of that high energy radiation you get from space. So now for our last category of an object, namely neutron star mergers. So when you have black holes or neutron stars, they are radiating off the, energy in the form of gravitational waves. As they orbit, the objects radiate off energy. That energy has to come from somewhere, so it makes the orbit shrink and they go faster as they get closer together and orbit faster and faster. Here's a video of a black hole merger. You see that the two objects start orbiting each other, and as they orbit, they lose energy, and they keep distorting the space around them, and they keep distorting it until, and eventually they get closer together, and they'll begin a merging process. These are black holes, so you're seeing the lensing around them as they orbit. As they get close enough, suddenly they hit their what they call a chirp, and they merge together in an explosion of gravitational energy. That burst of gravitational radiation energy is often on the order of a solar mass of energy being radiated out all at once. So, in other words, for a brief second, the gravitational radiation, or a brief fraction of a second, the gravitational radiation from these two objects merging outshines every single star in the universe put together. But that's just two black holes. They don't really do much more than merge because there's no matter around them. They're just lumps. They're just a relativistic object where it's just a black hole. You get more interesting things happening when you have a neutron star merger. So here's an example of neutron stars merging. You'll see the two orbit one another, but they actually have physical matter that can interact. So when they collide and merge together, they create a massive explosion. So here you see they get closer together, they radiate more and more gravitational energy. That makes them speed up and move closer together. And when they collide, they're moving at a significant fraction of the speed of light. And that blows everything up. That explosion just throws a bunch of matter off into space, causes some extreme environments, and it probably creates a black hole. So we've seen this happen. In one specific instance, we saw a neutron star merger, or rather we heard it. LIGO detected it with their special detectors. The two of them together saw the merger. So here's a plot of the gravitational merger. You see gravitational waves happening right here. As time goes forward, the waves slowly accelerate until they merge. And then right here, about a second or so after the merger happens, there's a massive explosion, and several different gamma ray instruments saw a gamma ray burst. So basically, LIGO detected the merger of two neutron stars, and about a second after the merger, in the right region of the sky, both Fermi and Integral saw a gamma ray burst. In other words, light was produced by this gravitational wave event. And the best thing is that this actually helped us localize the event. So with just LIGO's two detectors, Hansford and Livingston, that's the H and L thing in the green dashed outline, they'd be limited to two curved regions of space. Adding in Virgo gives you the green circle. But then you can also confirm that everything is correct by looking at the localization from Integral and GBM. And you'll notice that every single one of those contours, or those air regions, line up perfectly. In other words, while no one got the localization perfect, everyone's in agreement about where it happened generally. And by combining them, you get an even better picture of where it had to have happened. So in other words, by just looking at a combination of mergers and looking at it in both the optical gamma ray, X-ray, all the light-based bands, and for gravitational waves, you get a good picture of what happened. Two stars merged, and that explosion created a gamma ray burst and a distinct afterglow for about a month afterwards. This also was another source of heavy elements. When two neutron stars merge, the explosion is so extreme, it can create heavy elements. Notably, it's the source of all of the gold, or almost all of the gold, and all of the uranium and plutonium and actinium and thorium in the universe. If you have uranium, if you have gold, thank an explosion, thank a neutron star merger. Without that extreme event of two neutron stars literally spinning into each other, colliding, and blowing up, you would not have heavy elements. You couldn't have uranium. You couldn't have gold, platinum, iridium, osmium. So that is why we care. That is a bit about what you can do with multimessenger astrophysics. You can look for a correlation of events, and you can see from that the coincidence between a gamma ray burst and emerging neutron stars, and then from that you can then deduce the production of heavy elements, more heavy elements. So basically, multimessenger astrophysics is a great way to get additional information on the most extreme environments in space. It let us understand how the core of a star dies, how stars explode, how heavy elements are created. We've identified a few sources. Almost half of the unknown sources have been discovered recently, in the last few years. And of course, as time goes on, we'll get better at this. We'll find more sources, and our methods will improve. So the future is bright for multimessenger astrophysics. With it, we can see extreme environments. We can learn a lot about the cosmos, and we'll get better at it as time goes on, because we're still working out some of the kinks and getting better at it as we go along. So thank you, everyone. I believe if people have questions, you can ask them now.
Yes, Colin, thank you. If you want to unshare your screen, we can get to the Q&A section. So there's a bit of a delay in the stream. So of course, that also means that I get to ask the first question as the MC. So LSU is one of the few physics departments that have all four messengers represented in the department. We have an astronomy group, we have the group at LIGO, we have a neutrino group, and we also have a cosmic ray group. Is there any fun stuff that you think that all four of those, large, all-encompassing groups could do together at LSU?
All four could do together? Maybe. The more you add in, it gets harder. Probably what you could do, you could do some work with identifying the composition of the cosmic ray spectrum. That could help you identify what elements are being accelerated in like a blazar or an active galaxy. So you could identify what because currently we don't know exactly what elements are being accelerated. We assume protons, but there's evidence there's a lot of iron being accelerated and other elements. And knowing exactly what you're looking at is important. Problem is when the ray hits the atmosphere, it blows up and we only see the secondary effects of the explosion. I mean, explosion is not very powerful. It's barely the equivalent of a light bulb, but it still happens. So if you get more information on composition and then you see some more coincidences between blazar photons and blazar neutrinos, and maybe even gravitational waves and maybe even if that would probably get you some information. I'm not sure you can necessarily get gravitational waves from a blazar. Potentially, if you had a gravitational neutron star merger, you could see neutrinos from that. Maybe cosmic ray evidence. Maybe you can get some cosmic rays from that, and almost certainly you could see neutrinos. We haven't yet, but it's theorized we should see them. We just haven't yet, so we're still looking for that.
Isn't that the quote of all astronomy? It's we should have seen them, but we haven't yet.
Yeah, but if as time goes on, you either have to revise your theory about what you should see, or you find it eventually. That's happened, and both have happened in history. Either we found it, or we had to change everything because we didn't find it at all.
Well, we're also due for a supernova in our galaxy. You think it's going to be Betelgeuse?
Betelgeuse is going to go nova eventually. Problem is, it's an astrophysical time, which is to say it could go tomorrow. That's unlikely, but it's probably going to go more likely in the next few thousand years. There could be another one that goes before it. We don't know. There's a lot of possibilities. I'd love to see it go supernova. When? No one knows. We'll have some advance warning before it goes, but that'll only be a few hours or maybe a day.
Yeah, well, we'll probably be all right. Probably.
Yeah, I'm looking forward to it happening, but I cannot tell you when. Just that we'll know only very shortly beforehand.
All right.
Also, when Betelgeuse goes, it'll be visible during the day.
All the better. All the better. We'll have a second sun. So Lisa Diekman asked, Colin, do you have a favorite extreme event in the universe?
Good question. I am very fond of just blazar flares. Because all we're having there is the active galaxy just starts accreting more material and the flare heats up. And yeah, blazars are extremely variable. So the blazar flares are amazing things where, it can suddenly triple its brightness or get 10 times brighter in the space of a few minutes. And then it can go back to being normal again for in minutes later. So they're highly irregular. And I'm also glad that we're not near them. Yeah. There's some... I was looking, when I was doing my graduate studies, I looked at a blazar called Markarian 421. And if it were like near our galaxy or even in our galaxy, it would just be like nuclear bombs going off every part of the atmosphere simultaneously from the amount of energy it would be depositing from its jet. They are insane.
In your talk, you mentioned a lot about a variation of things that if they were closer to us, we'd probably be dead immediately. But yep. One of the brightest sources in the sky, at least for X-rays, is the sun. Is it bright in cosmic rays and neutrinos as well?
Yes, it is. It's the first source we had of both of those, actually. Solar flares were identified as a cosmic ray source back in the 40s. And we saw solar neutrinos back as far back in I think the 80s. I'll have to check the exact date of that, but yes, we see both from there. Once again, the source is a significant X-ray source, not because it's very bright or energetic, but because it's close. And if the sun, so it's similar to the fact that the star Sirius is bright mostly because it's close to us. It's not actually an abnormal star in any way. It's just close. So in most cases, stars like that, so the sun is certainly a significant X-ray source, but thankfully our atmosphere stops it out, and we're not going to, it doesn't instantly kill us. Without an atmosphere, we would certainly be a lot more dead from radiation, as well as not being able to breathe. This is actually of significant concern to a mission to Mars. The increased solar radiation and cosmic radiation you'd receive from the spaceship is considered a threat to survival.
Yeah, we actually had an AOT talk from Jeff Chancellor, who's an LSU professor who works specifically on, dose radiation from spaceships and stuff like that. So we have a tradition in our questions here. Tabby's son, Jude, asks, what is your favorite Pokemon?
Not sure I have one, but I really like Mamoswine and Ampharos.
All right, solid choices. Benjamin Eunice, who's on our staff side here, asks, if you could ask the universe one question to be answered immediately, what question would you ask?
Oh God, that's so many questions to ask.
Very philosophical.
Might just might try to just figure out I'm probably just asking the big physics, the big fundamental question about the nature of physics, namely, how do you go about unifying relativity in quantum mechanics?
I'm sure that the quantum gravity group at LSU would love to also know that answer.
Yeah, that's the $1 million question. Literally.
Okay, well, with that, we're gonna go ahead and break to intermission. If you have more questions for Colin, please put them in the chat. I believe he's on the stream, so he can answer them through that, if that's okay. Are you all right?
I can certainly answer. I can answer questions to this on the stream. I'll pull it up once I no longer have the feedback worries.
Yeah, no worries. But in the meantime, we're gonna break to intermission. While we're gone, just go ahead and, if you feel so inclined, feel free to donate to our Venmo or PayPal. Again, our tip war this month is, do you think the phosphine detection on Venus is real life, or is it just spooky geological processes that we don't know about? We're also going to be sharing some slides with some fun facts while we break, so that you aren't just staring at a screen. So feel free to test yourself with those, but we'll be back in about 5 minutes. It's kind of a weird time because it's 7:42 on my clock, so I guess we'll be back around 7:47, which is a very awkward time, but we'll be back then, and we'll have Donna with us, and then we'll get started on the second talk, okay? All right, see y'all in 5 minutes. Alrighty, welcome back, everyone. I have with me today an astronomy professor at Mississippi State, but don't hold that against her. She's currently on sabbatical, sharing her time there and at Auburn, Alabama, so also don't hold Auburn against her. She's also worked at NASA's Deep Impact mission on the Comet Tempel 1, and she's our second speaker tonight. This is Dr. Donna Pierce.
All right, thank you very much for having me, and I will start sharing here. So, given that most of you are in the Baton Rouge area, I thought, and comets don't have a big presence in your department, I thought I'd talk a little bit about my area of study, which is comets, and give you guys something different. So comets, which are sentinels of the outer solar system. And so as far as this presentation goes, I'm going to introduce you to a little bit of the history of comet studies, why we consider them important, and where we want to go with comet studies. And just for added fun, this picture here that you are seeing is actually a picture that I took of Comet Neowise, which was our fantastic comet this past summer. This was actually taken from the MSU campus in Starkville back in early July. So throughout history, comets have fascinated all of humanity. Whenever they have made a notable appearance, they have no doubt produced a lot of awe and wonder. They've also produced a lot of terror. Many pieces of art have been devoted to them. Many historical events have been depicted with them in the background. And so they've had a part to play not only in terms of human history, but also in terms of the history of our own solar system as well. Now, throughout much of history, comets have been associated in the mind of the public with something more like what is depicted here in this image from 1857, and that is the idea of comets being omens of doom and destruction. And that's because throughout history, certain events, the birth and death of kings, for instance, have been connected to certain comets that have been notable. However, these days, thanks to modern telescopic observation and computer-driven observing campaigns, we discover so many comets now that you could tie an appearance of one of these to anything, including the birth of your cat, if you really wanted to. We know about over 6,600 comets in our solar system. There are very likely lots more, many of them locked up in certain regions of the solar system that I'll talk about here shortly. But in terms of history, I want to proceed with a few historical notes of interest. So it's very interesting to study the history of comets as well as the science. And I'm going to highlight three people in particular for my notes here. The first one is the great Danish astronomer Tycho Brahe. He lived between 1546 and 1601. And for those of you who are less familiar with the history of astronomy, he died before the year 1609. And the year 1609 is significant because that's the first year that a telescope was documented as having been used for an astronomical purpose. And that was by the astronomer Galileo. So Brahe was one of the last of the great pre-telescopic astronomers. He was very rich. He funded his own private observatory on a small island in the Baltic Sea. And there he amassed some of the best data that were available at the time on star and planet locations, which would ultimately lead Kepler to devising his laws of planetary motion, which still hold today. But one of the other things that Brahe did in terms of comets specifically was that he determined the distance to a comet that appeared in 1577. And what he determined was that the distance to this comet was more distant than the moon. And that's significant because at the time, it was not entirely clear to astronomers whether or not comets were atmospheric phenomenon or celestial. And so with his determination of the distance to a comet being more distant than the moon, that established definitively that comets were in the celestial realm and not atmospheric. Fast forward in time to Sir Edmund Halley, who lived after telescopes came into use and when geocentrism was dying in scientific circles. Now, at Halley, that name may be familiar to any of you who know anything about comets, and I'll get to why here in just a minute. But one of the things that he contributed to this field was that he determined that comets that appeared in 1456, 1531, 1607, and 1682 were in fact one in the same comet. And he predicted, although he did not live to see the prediction borne out, but he successfully predicted that this comet would return in 1758, which it did. And this comet is now known as Comet Halley in his honor. So it has a revolution period of about 76 years. So, very comparable to a human lifetime. The last time it made an appearance was in 1985, 1986 timeframe, and will reappear again in 2061. But one other person that I would really like to highlight is an American, and her name was Maria Mitchell. And she founded the astronomy program at Vassar College, and she's one of the great early US scientists. Back in 1847, she discovered a comet using a telescope, and it's now known as Comet Mitchell. But the reason this was significant is because there was a prize that was issued by King Frederick VI of Denmark, and he was kind of a Richard Branson-like character. He had an intense interest in science, and so he founded a prize for anyone who discovered a comet using a telescope. Well, in 1847, an American, Maria Mitchell, would win that award, thus beginning to establish robust American contributions, not only to science in general, but also to astronomy. Now, the reason that I'm now going to segue into reasons we study comets now. Now, this image here is an image of Comet Hale-Bopp, which was a great comet that came through in 1997. And I was in college at the time, and I remember seeing this, and it was so bright in the sky, there was no question as to where to point the telescope. And when you have comets like this that come through, it's great because it not only generates public interest, but also a lot of observing time gets devoted to these objects. But anyway, just a little bit to give you an idea of the basic anatomy of a comet. Comets actually have two tails, and we're seeing both of them here in this image. The one on the left, which is blue, is called the ion tail. And I'm going to come back a little bit later to this particular tail. We're going to talk about it a little bit more. The other tail, which is off to the right and looks white in this image, is called the dust tail, and gets its name because it's loaded down with dust. Now, this stuff is produced by the comet when it approaches the sun. So as this body approaches the sun, what happens is the ices inside this body begin to heat up, and they heat up to the point that the ice turns straight to vapor. And this vapor produces the head, which is the semicircular area seen down lower left, and these magnificent tails. Now, depending on how active the comet gets when it approaches the sun, these tails can stretch for many millions of miles long. And the head of the comet, which is down here lower left, can be tens of thousands of miles wide. Now, in certain rare instances, these heads of comets can even briefly become larger than the sun itself, which has happened from time to time. Now, deep inside the head of this comet is the nucleus, which is the solid body where all of the ice is originated and all of the dust that goes into the dust tail. Now, what is amazing is that deep inside that head is this small solid body. Now, you can't see it in this image, and that's because all of the brightness of the sunlight reflected off of the dust is obscuring our field of view. But thankfully, we live in the age of space exploration, and we are now capable of launching spacecraft to these objects, so we can actually see those solid bodies deep inside the head, what we call the nucleus, up close and personal, which we have done now 6 times. So, starting with the appearance of Halley in 1986, we started launching spacecraft to comets. And what you're seeing here are either mission badges or artist depictions of the spacecraft that have been sent to comets. Many of these are NASA missions, but not all of them are. Some of them are European and some are from the former Soviet Union. But regardless of the origin, which country they're from, they have all taught us very valuable things about comets. And we are still analyzing the data from them today. As a matter of fact, I still regularly get asked to read proposals that are submitted to NASA with new ideas of things to do with some of the data from these older missions. So don't think these things are dead and buried. They're still giving us scientific returns. But as far as being able to see those nuclei deep inside the head up close, this is what spacecraft have been able to get us. So these are 5 of the 6 nuclei that we've seen up close and personal. So we can't see them from the ground because all of that dust obscures our view. But also when you look at the sizes that are shown here on the 5 comet nuclei that we've seen, so Halley, which is here upper right, which is the first one we saw when it came through in 86, you'll notice that the distance bar there across its longest extent, it looks like a potato-shaped body, is 9 miles long. So yes, just 9 miles. And some of the other comets that we visited, Comet Tempel 1, which was the target for the mission that I worked on, barely 5 miles across along its longest extent. Comet Borrelly, just over 5 miles long. Wilt 2, which was the target of the Stardust mission, which actually took dust particles from a comet tail and brought them back to Earth for lab study. Comet nucleus barely 3 miles wide. And most notably, Comet Hartley 2, which used the recycled Deep Impact spacecraft to visit a second comet several years after it visited Tempel 1, visited a comet nucleus that was just barely over a mile across. So in addition to dust obscuring our view of these nuclei that we would love to get to know personally, you will notice that these nuclei are only a few miles wide. So you put them out millions of miles in space, they're going to be very hard to see, even if there isn't all that gas and dust there. But even more notably, and what is very hard to see in these pictures, is their reflective properties or lack thereof. So these comet nuclei are so dark that they have the same reflective properties as the black toner in a photocopier. That's right, they only reflect about 2 to 4% of the light that hits them. So they're dark, they're tiny, and you put them out in millions of miles of space against that coma, they're very hard to see. And that's why we have been blessed to be able to learn so much, not only from ground-based and orbiting telescopes, but also missions to actually visit these objects up close. And we want to continue to do that into the future. Here is the sixth comet nucleus we've seen up close, Comet Churyumov-Gerasimenko. Once you've said that once, you've had the right to call it CG every time afterwards. This was the target of the recently completed Rosetta mission, which was a European mission to very intensely study this comet as it came in close to the sun. We wanted to see how it's all the gas and dust coming off of it would grow and change, both chemically and in terms of the physical dynamics. We wanted to study everything we could about the nucleus. So we had a spacecraft that orbited around it and a tiny little lander that was supposed to land on the comet and return data. Instead, it hopped a few times and landed on its side and did not get us much of a return. But nonetheless, this is the nucleus, and just like the others that you saw, it's irregularly shaped. And again, it's only a couple of miles wide, so it's a very small body. And yes, if you are thinking that this thing looks like a rubber ducky, you are in fact correct. That is in fact the basic shape of this nucleus. As a matter of fact, when we refer to different parts of this comet, instead of using the term hemisphere like we're used to with talking about Earth, we would refer to the pieces as hemiducts. Now, given the images that you've just seen of the comet nuclei, those of you who have seen pictures of small bodies in the solar system might be saying, gee, some of these look kind of like pictures of asteroids that I've seen. What differentiates an asteroid from a comet? This is a question that I get a lot. And so on the screen here, you're seeing an asteroid as compared to a different image that was taken of Comet CG. And so you'll notice that they are both irregularly shaped and they do both look rocky. And that tends to throw a lot of people off. But one of the things that distinguishes a comet from an asteroid is that fuzzy stuff that you see that comes off when when the ice is turned to gas. And so it forms that atmosphere, the head of the comet and the tails, and that you don't see with asteroids. But another thing that distinguishes them is where the vast majority of them are located in our solar system. They tend to occupy different regions. So here is an artist's depiction of the sun and the 8 planets. And for those of you not familiar with the structure of the solar system, going left to right is the order of the planets from the sun. They are shown to size scale, but not to the appropriate distance scale between them. The inner 4 planets, Mercury through Mars, should be situated much closer together and much closer to the sun on the left. Jupiter through Neptune should have a lot more spacing between them. This is something that also tends to throw a lot of people off, particularly intro astronomy students, whenever you show an image like this. But most asteroids in our solar system are located in a region between Mars and Jupiter, and this region is called the asteroid belt. And we started finding objects out here starting in the year 1801. And there are now tens of thousands of bodies out here known, and we discover new ones all the time. Now, if any of you have seen the movie The Empire Strikes Back, you know that there is an asteroid field as part of that film that Han Solo and them have to navigate through to avoid detection by the Empire. That is a very false sense of what an asteroid belt is actually like. The distance between asteroids in the belt is considerably larger, so it's not like what you see in the film. There's vast space between the asteroids, and to get to any one of them, you have to get there intentionally. But most of the asteroids are located there between Mars and Jupiter. Most comets, on the other hand, tend to come from 2 regions that are much further out. And the first region is a region that Pluto belongs to, and several other bodies that we started discovering there starting in 1992. And this region is now known as the Kuiper Belt and Scattered Disk region. And it starts at around Neptune's distance from the sun, which is about 30 times larger than the distance between the sun and the Earth. And it goes out to about 1,000 times that distance. And that is thought to be the region where a lot of comets that have orbits less than 200 years come from. That's their ultimate origin. And some of them probably formed there when the solar system formed, but many of them were scattered there, basically slingshotted gravitationally by Jupiter and Saturn and Uranus and Neptune as they were in the process of building up. So we think comets represent an earlier stage in the process of going from gas and dust in space to building up a solar system, to forming things like the giant planets and the terrestrial planets, the Earth-like planets. So there's a lot about the formation of our solar system we don't understand, particularly how to form the giant planets, Jupiter through Neptune, to the right mass and on the right time scale for other things that we know have happened to have happened. And so one of the ways that we study the solar system is to not only look at the other ones that are now being found, the so-called extrasolar planets, but also to take a look at the leftover bricks and mortar that went into our own, and that includes comet material. Now, not all material that was slingshotted got slingshotted into this region here. There's another more distant region that we think exists very far away from the sun, even further than the heliopause, which is the termination of the effect of the sun's radiation, the solar wind. And this region is called the Oort cloud, and it's basically a spherical shell that surrounds the entire solar system and stretches almost a third, if not about halfway, to our nearest neighboring star. That's how far away this thing is. We've not actually seen the Oort cloud, but we've inferred its existence based on orbits of comets that take many tens of thousands of years to revolve around the sun. So we would eventually like to detect it, but so far no spacecraft has gotten that close to it. But we think that the Oort cloud is the origin of a lot of the comets that take a long time to go around the sun. I showed you a picture of comet Hale-Bopp earlier. Hale-Bopp is a good example of such a comet. And we think that interaction with the larger galaxy, known as galactic tides or passages of nearby of stars at some point in the past, probably brings those objects into the inner solar system, which is where we then start to see them. But this idea of comets representing leftover bricks and mortar that go into building our own solar system is one of the reasons why we want to study them. Again, to understand the process of forming a solar system in greater detail. And we also want to connect comets to other regions of gas and dust in space, which is known as the interstellar medium, or ISM for short. It's in regions of the interstellar medium where the star and planet formation process begins. And so one of the ways we try to connect our own solar system to the interstellar medium and to the other solar systems that we're now finding is through chemistry. And so it's very important for us to understand the chemistry of comets, and comets are very rich chemically. So there's basic chemical information already locked up just in these two images right here of two notable comets that came through in the late 1990s, Comet Hyakutake and Comet Hale-Bopp. Now, the reason that I say that, and I apologize if any of you have issues with color perception, so I'll sort of guide your eye here. But if we take a look at the image of Comet Hyakutake on the left, if we take a look at the head of the comet here, you may notice that the head looks a little bit greenish in appearance. Well, that is not an accident. That greenish color is very indicative of a particular molecule. And this is called C2. It's two carbon atoms that are bound together. And we see this molecule a lot in comets. And we have seen comets like Hyakutake and several others, including Comet Ison and Comet Lemon, in the last decade or so that have been notable for having these bright green heads. And what that's telling us is that this comet is very rich in carbon chain molecules. On the right, this image of Hale-Bopp, and now that's where we're going to come back to that ion tail that I showed you earlier. You'll notice that that ion tail is blue, and that's not an accident either. That color is telling us that the ion tail is rich in a molecular ion. So it's a molecule, but it's an ion because it's missing an electron. And in this case, the molecule is CO+, which produces a lot of blue light in the visible spectrum. So already we're getting basic chemical information just from these images. Now, to get more detailed information, you've either got to send a spacecraft to fly through the atmosphere to gather the data, or you have to take the light that's coming from the object, and after it goes through your telescope optics, pass it through a device like a prism or a diffraction grating, which can split the light into its constituent colors. And we analyze the colors to look for chemical signals. This is known as spectroscopy. And with spectroscopy, we've been able to find a lot of chemicals in comets. So this table here is taken from a paper that was published 9 years ago by two other notable comet scientists, Mike Muma and Steve Charnley, which lists several chemicals that are commonly seen in comets. Now, these chemicals are notable because they actually come directly from the nucleus itself. Unlike the C2 and the CO+ that I showed you in the previous slide, which are results of these molecules in this table being broken apart by solar UV radiation. But at the top of the list here is water. Water is by far the most dominant chemical in comets. After that, you have carbon monoxide and carbon dioxide as your next dominant chemicals. Now, this table is grouped such that it includes various groupings of things together. So in the next group down, you see something called CH4 and C2H2. Those collectively are known as hydrocarbons. And on Earth, we think of them as very flammable things like methane, ethane, and acetylene. Those are very frequently seen in comets. In the next group down, you will see a group starting with CH3OH, that is known as methanol, and below that is H2CO, which is known as formaldehyde. We have seen those molecules in a number of comets as well, and they are grouped together with a group of other notable large molecules that are considered organic. By the way, the chemistry definition of organic means that they have carbon somewhere bound within the molecular structure. The next group down contains molecules that are rich in nitrogen, the most notable one being in the top of the group here, NH3, which is ammonia. The final grouping at the bottom of the page is comet molecules that are rich in sulfur. So we see a number of sulfur-rich compounds as well. So taken together, what you can see is that comets are very rich chemically in a number of molecules, many of which are organic. And so we think comets may have had some part to play in the origin and development of life on Earth, but what exactly that role is still up for debate. But among some of the other interesting things that we have found, both through ground-based and flyby spacecraft data, is that we've actually confirmed that the water that we see in the atmospheres of comets is linked to water ice in the nucleus. That was seen definitively for the first time with the Deep Impact mission to Temple 1. That's when we first actually saw water ice in the nucleus of a comet. Other interesting molecules that we have seen chemically are ethylene glycol. And for those of you not familiar with that chemical, that's the active ingredient in antifreeze. We've even seen an amino acid in a comet. The amino acid glycine was seen in comet dust samples that were returned from the tail of Comet Built 2. So we've now actually seen one amino acid in a comet. But we've also seen other interesting complex organic molecules as well. Most notably, we have seen signatures of what are called polycyclic aromatic hydrocarbons, or PAH for short. These are very large molecules and they are organic. They do have carbon bound within them. And for those of you not familiar with them, if you've ever eaten a burger or hot dog from your backyard barbecue, you've likely ingested them. They are a byproduct of the grilling process. And yes, they are carcinogenic. So what we see is that comets are very rich chemically, and many of these chemicals have also been seen in different parts of the interstellar medium, albeit in different abundances than what we see in comets. Some recent highlights, two comets that have made news within the last year or so are comets Borisov and Neowise. Comet Borisov, which is shown here on the left, is notable because we've now established that it did not come from our own solar system. That's right, you heard me right. Its orbit is one of the most extreme that we have ever seen. We have now labeled this an interstellar object. It does not come from the Kuiper Belt scattered disk or Oort cloud. It has come from interstellar space. And so far, a chemical analysis of it has shown that it is very depleted in C2, which we saw very abundantly in Comet Hyakutaki's head, the bright green. But you'll notice that this image is very blue. And that means that this comet is very rich in carbon monoxide, one of the richest we've ever seen. Now, on the right is Comet Neowise, and this made headlines because this was our great comet of the summer of 2020. And hopefully some of you got to see it either in the morning sky in July or in the early evening sky in late July, early August. But Comet Neowise was discovered back in March and achieved naked eye visibility in early July. And we're still learning a lot about this comet. Not a lot has been made available in terms of research yet on this comet. But one thing we've also noted is that, like Comet Borisov, it is also very depleted, very low abundance of C2, unlike Hyakutaki, which we saw was very abundant. So we're continuing to study these comets to see, are they rich in certain chemicals? Are they poor in certain chemicals? And if so, what is that telling us? And some of this may have to do with the place of formation, how close they may have formed to the sun, or it could be telling us that some of them formed earlier in the solar system's history than others. Those are still some ongoing questions that we are struggling with as we continue to amass data on more and more comets. So we're hoping that as time goes forward and we're able to gather data on more comets, our statistical analysis will be better and we'll be able to say more about these types of intercomparisons that we want to do. So where we're going from here, there is no current active mission to a comet right now. However, the European Space Agency just recently approved a new mission called Comet Interceptor. And this is a screenshot of its website right now as of today. And you'll notice there's not much here yet, and that's because this mission is still in the very early stages of development. But what we would eventually like to do is study more comets up close and personal, like we have with the 6 nuclei that I showed you earlier in this presentation. This would be a robotic spacecraft. It would sit at a point a little bit further from the sun than the Earth. It's going to sit at about the same point that the JWST telescope will sit. And it will park there until we have an appropriate comet target that will come along, preferably a comet that's a first-time visitor to the inner solar system. That would be the desired target. We would then send this mission, the spacecraft, to this comet to study it up close and personal. So we're hoping that if all goes well with this, we'll be able to study several more comets up close and personal with the Comet Interceptor mission. So with that, I will summarize here and wrap things up. But hopefully you will be in agreement with me that comets have fascinated us throughout history, and they continue to fascinate us today, both in terms of their beautiful physical appearance, but also the deeper beauty that underlies them, their physical and chemical properties, and how we can link them to our own solar system and to interstellar space. Their physical and chemical properties, like I alluded to earlier, may provide insights into how solar systems are made. In particular, a lot of these comet bodies formed in the same region of the solar system as the giant planets. Their formation is poorly understood, so we're hoping that a better understanding of comets will lead to a better understanding of how to make planets like Jupiter through Neptune. Ongoing ground-based observations and robotic space missions need to continue to work together to understand the nature of comets. So anytime we have a mission, we do more than just send the spacecraft there. We have an armada of ground-based and orbiting telescopes that will also look at the comet, both in visible light and the non-visible forms of light that Colin alluded to in his earlier presentation. So that way we can study these things from every conceivable angle and hopefully answer our ongoing scientific questions. All right, thank you very much for your time and attention, and I will stop here and take any questions that you may have for me. Thank you very much.
Yes, thank you, Donna, for a wonderful talk. Very detailed, a lot of stuff in there. You mentioned early on how Hale-Bopp was like super bright, and that brought a lot of public interest into comets. Can you talk about why you think that's important to science and why that's a good thing to have?
Oh, well, definitely for a multitude of reasons. First and foremost, when you have events like that, particularly with children, if any of you know anything about science education, many scientists got hooked at a relatively young age. The majority of them did. And that hook tends to happen before the age of 12 for most of them. And in particular, if you share this with the broader public, you're not only capturing the public's imagination, but in particular, you're getting the next generation interested in science, whether they go into astronomy or a different field. That hook happens. And with events that are spectacular like that, it's very easy to hook people of all ages on them. So for one thing, it's recruitment of the future generation of scientists. And in my case, it wasn't a comet, but it was the Voyager spacecraft images that hooked me. During a lesson on the history of space exploration when I was 10 years old. So it's events like that that will, in part, help us recruit the next generation of scientists to help us pick up where we live off. But also, it gives us a chance to engage in dialogue with the public about how their taxpayer money is spent. So among other things, you'll notice I mentioned NASA a lot, and NASA is taxpayer funded. So among other things, you'd like to know where your money is going. And we are lean meat. For every dollar invested in endeavors like this, you get many more dollars back, not just in terms of the basic science, but also the softer effects, the technologies and stuff that get invented that eventually end up as part of our lexicon. Like, for instance, the CD and the DVD. You have in part the Voyager missions to thank for that. And even we in astronomy tend to push imaging capabilities to the point that medical imaging benefits from us. As a matter of fact, I was talking with a medical imager a year ago, and as soon as he found out I was an astronomer, he shook my hand. He said, "We have so much to thank your field for, because it's your advances, you pushing the limits, that have benefited the medical field." So yeah, it's popular events like that. Yeah, not only for recruitment, but also the chance to show off where taxpayer money is going. And also, since I do also enjoy a lot of artistic endeavors as well, it's also fun to see folks in the creative professions, how they interpret the things that are going on. What artwork, what music, what poetry also gets generated as a result of this type of inspiration.
Very nice, very nice. So we'll get started with some questions from the audience. Noelle Rabina has a few questions. The first one is, who do I call if I discover a comet?
Okay, so let's say that you have discovered something that you think may be a comet. First of all, make sure you get at least 2 subsequent nights of observations to make sure it's a moving object. um, and it seems to be moving against the background stars. But once you are convinced that you've got something, then you want to put in a call to the Central Bureau for Astronomical Telegrams. And you want to put your mark on that discovery. And you'll be asked to provide basic observation data. So they'll need to know things like the celestial coordinates, RA, right ascension and declination of your target. And once they have that, they'll establish, and the date and time of your observation, they'll establish that as a possible detection. There will be calls put forth to do follow-up work as independent confirmation, but assuming that you're the first documented person, then the International Astronomical Union's convention for naming comets is that they're named after the discoverer. Unlike planets, which are named after Greco-Roman gods and goddesses, or surface features on Venus, which are now named after women, the International Astronomical Union convention for comets is that they're named after the discoverer. So if you get that earliest timestamp in, you get your name on it.
Everyone now has a goal that they need to achieve.
Yeah, so put that on your bucket list.
They also ask, what's the next comet coming up?
Oh, good grief.
So many.
Yeah, so many. There are many of them. Unfortunately, an immediate name is escaping my mind at the moment.
That's okay.
But even if you can't catch a comet, you can always catch their effects. So if any of you are familiar with meteor showers, they are the debris left by comets. So that all those dust tails that you saw in the images that I showed you, that debris gets left behind, and when Earth passes through it, we get meteor showers. So, for instance, one of the most famous meteor showers that you'll see occurred back in August, the Perseids. And I name those because they're typically consistent in terms of visibility from year to year, whereas others are more hit or miss. But anyway, that's all debris from comet tails. So if you can't catch a comet, you can always catch a meteor shower.
Very good, very good. L Cuban 0292 asks, do we need to know the nucleus size in order to determine the number of orbits left in the comet's life?
Oh, in part, yes. In part, the size is going to drive how much material is there. So obviously, just logically speaking, the bigger the object, the more likely it is going to have material that will last the comet many, many passages around the sun. But what's interesting is there's still a lot about that outgassing process, that process of producing all that fuzziness that we still don't understand. Most notably, there is a comet named Comet Encke, and it's spelled Encke. Comet Encke has the shortest revolution period of all comets, 3 1/3 Earth years. It has been around the block many, many times, and it is still going. So one of the big questions we have about this process, and that plays into your question, is how can a comet survive so many passages around the sun and still be spewing this stuff out? And that's something we still don't have a good handle on. As a matter of fact, up until the early 20th century, we weren't even sure that comets had a solid body, a nucleus, as I've alluded to. It used to be thought that comets were a collection of particles loosely bound together that just traveled through space together. We called it a sand bank. But in the year 1950, astronomer Fred Whipple came up with a new idea for comets, and it was based on Comet Encke. He said the only way that he could conceive of a comet lasting so long was if all that material came from a central solid body that was small but considerably denser than the fuzziness that we see. And that became known as the icy conglomerate model for a comet nucleus, which is more commonly known in public speak as the dirty snowball. this mix of ice and dust. So in part, it's that conglomerate nature that helps it hang on for so long, but also the entire surface isn't active either. We know that only certain portions of it are, but still, as to why comets like this can last for so long is still a mystery.
Very good. We have another question. This one's from Courtney Hill. Was there a certain point or event in your life that you knew you wanted to dedicate your studies to astronomy and or comets?
Oh, all right. So this goes back to something I mentioned towards the end of you talking about engaging with the public here. So in my case, I was one of those folks who got hooked on science at a very young age. I happened to grow up next to a lake, and in my early elementary years, I was fascinated by biology. And my mother and my father are also scientists by training. And we would often grab pond water, lake water samples from our backyard. And my parents gave me a microscope. And we had fun looking at all the one-celled organisms that were in the water in our backyard. So that's one of the ways I got hooked on science. But how I got hooked on astronomy specifically actually was through a social studies class, not a science class. We had a social studies unit when I was 10 years old on the history of space exploration. And one of our lessons was about the Voyager 1 and 2 spacecraft that visited the giant planets. And it was when I saw those images, and specifically it was the image of Saturn with all of its moons in this giant, incredible mosaic, that there was a voice in my head that said, that is what you're going to do. And that's when I didn't look back.
Very
and
good.
That's when I was 10 years old.
If you're into old science photos from historical missions, you should talk to our streamer Allie. Her dad developed all the photos from the Apollo 11 images. So
oh, very nice. Very nice.
We also have a question from Michael Bryant. Does NASA or any other space agency have any plans to send another lander onto a future approaching Earth comet?
We definitely would like to. As a matter of fact, the ultimate goal is a comet nucleus sample return. Now that is a very lofty goal. So some of you who might follow astronomy and space news may know that we have a mission to an asteroid right now, where they're going to return an asteroid sample mission. That mission is named OSIRIS-REx, and they want to return a sample of an asteroid named Bennu. We want to learn more about the physical construction of the rock as well as its chemical composition. We would like to do the same thing for a comet, but comets present extra challenges largely because of that outgassing effect. If you want to collect a sample from a comet, you got to do it when it's far enough from the sun that your spacecraft isn't going to be blown away from the nucleus by all of the outgassing. And when the Rosetta mission tried to land the lander on Comet CG, they had to do it when the comet was at its point furthest from the sun, where you would reduce the probability of the stuff of the lander getting shot off of the nucleus by outgassing material. So yes, the ultimate goal in the foreseeable future is to do what's called a comet nucleus sample return. And that would potentially involve a lander or something else that could hover above the surface and grab a quick sample. But right now, there is no call from NASA for a mission in the right cost class.
Mm-hmm. Yeah.
We're waiting for the next opportunity when NASA offers up a call for proposals for a big flagship mission, because NASA has different categories of missions. The one I worked on, Deep Impact, was a Discovery class mission, which is considered a cheap mission monetarily. You can't do a comet nucleus sample return at that cost level. It's one of those once a decade type things that NASA would do. So we're just waiting for an opportunity when that appropriate call comes out, and hopefully that type of mission design would win the competition. And it's a
Okay.
very competitive process. I've actually been part of mission evaluation for selections. So it's a very intense process that the teams have to go through. So even though an idea may be proposed, another idea might win out.
Yeah, that such is the life of an astronomer. It's eternally proposing time and just hoping you get it.
Yeah.
Um,
Yes. So, yeah, for instance, Deep Impact, which my advisor was the one who proposed it to NASA, did not get selected the first time it was proposed. He had to go through 2 rounds to get that one selected.
wow. Okay, so that is all the questions that I have in the chat, and probably all the time that we have. So I wanted to thank you, Dr. Donna Pierce and Dr. Colin Turley, for both having wonderful talks, and I want to thank all the viewers for being with us. If you're watching us asynchronously and not live, feel free to still interact with our video. Leave a comment, like the video, email us, reach out to our social media, whatever you want. We love to hear from everyone who loves the show. And don't forget to donate if you feel so inclined. Let us know in the comment of the donation whether or not you think the phosphine on Venus is life or not. Subscribe to our YouTube channel if you want to be on top of our next events. Check out our Facebook, Instagram, and Twitter, where we post about all of our events as soon as we decided about them. And for everyone who's local, please stay safe from Hurricane Delta, and we'll see you here on YouTube next month, where we'll have 2 more lovely speakers and maybe some new fun stuff to talk about. Thank you, everyone.